So let's try out some of these concepts on our model that we had already built. Remember, we had stored our predefined model in the object CLF, and we had fitted our matrix X of regressors onto our vector Y that says if someone survived or not on the Titanic. Next thing, we're going to import NumPy once again, and we're going to make a prediction and transform this into the NumPy format. Right? So to predict from your model if someone survived or not, given the information in X, we just use the .predict function that was part of the scikit-learn. And then what we're going to get here in this object training predictions is something where the model tries to recreate that vector Y. So based on this matrix X, and X could be new data, but in our case we're lazy, we're just using the data the model has already seen. And you should actually not do that, we'll talk later about why not. Based on that information, predict if someone has survived or not is in here. And now we're going to take the mean squared error of that versus the known survival in the vector Y. So nothing else than what we did in the hand calculation before. And handy enough, that mean square error function, you can also import it from scikit-learn, is also pre-built. So you don't have to do anything by hand here. And then what we're seeing is, wow, this is amazing. We're able to predict 97% of all the deaths and survivals in the data that the model has already seen. 97%, this is amazing, right? This is the blockbuster number that people would be running around the whole place and shaking up the whole company. Is 97% accuracy in my AI. Now the challenges, however, arise when we actually upload to Kaggle with the estimates on the test data. And remember, on the test data we don't know this Y, and the model has never seen the X for the test data, so it's new data for it. And we see suddenly on that unseen data there is only an accuracy of 74%. So imagine how that looks like in reality. You've just spent a huge portion of your life, significant cost to the company, to bring that amazing model into the customer's hands. As soon as the customers touch it, the predictions become horribly wrong as compared to what you had before. Don't get me wrong, 74% is still amazing, but of course you were expecting 97. So how can you protect yourself against this issue where you have high accuracies initially and then low accuracy in reality? Well, we know the most likely reason is there is still overfit. We talked about this and I was promising you overfit will come back to haunt us like a nemesis. So this is where we're standing right now, and what we kind of want to introduce is a stage in between that warns us, oh, I know on the data that the model has seen and learned from, you have high accuracy, but when I simulate the situation where you have unseen data, I think it's more towards that 74%, which we then see in reality on the test data later. So one thing you can do is you simply set aside a part of the data and you say, this is the data I keep unseen. I estimate the model on the rest of the data I have available, and then once I'm done with the estimation, I'm going to give it the unseen data and see how the accuracy is. And that's a good idea actually. Right? So we're going to use that concept, but to make it even more powerful, we're going to rotate what data we use as unseen. So that by the end of the whole procedure here, you will have simulated all parts of the data to be unseen at least once. Right? And this is known as cross-validation. On that unseen data, we then, for every single step, take the average error that we're seeing